Now we're ready to do a your turn question, and this is what I was starting to talk about just previously, 2 slides ago, is how the pressure does not depend on the shape of the container. So Pascal's vases is a demonstration equipment here where you have a certain number of vases, doesn't matter, 4 or 5, they all have different shapes. And at first this vase is empty. Now you notice that the bottom here, they're all connected. Water or any kind of liquid can flow here, it's all connected. So what you do is you fill up one of the vases, and to your surprise, when you fill it up with water or whatever liquid, then it's going to rise up each tube, and it's going to rise up to the exact same height. And this usually surprises students because they think that the more narrow vases would maybe have more water go up them. But the height is the same. So this question is a conceptual question, and it says, why is the water level at the same height in each vase? So this goes back to what we said a few slides ago. A couple slides, it said all points at the same depth must be at the same pressure. What that means is that down here, you're all at the same depth. You must be at the same pressure. The pressure is due to the weight of the fluid above, and what matters is the height of that fluid, because the pressure due to the weight of a fluid is rho GH. So you can see that they have to have the same height in order to exert the same amount of pressure at the bottom. If that doesn't make sense to you, another way that you can think of it is, well, what if the liquid in here was not the same height in each vase? What if this narrow one here, or let's say this one here, had a liquid up to this height? What would happen? Well, this greater height of liquid would mean that there's more weight here versus the other ones, more weight per area pressing down. There would be more pressure pressing down at C. The pressure at C would be more than the pressure at due to D here. Well, if the pressure at C is greater, that means it's going to push the other liquid up more because there's more pressure. And it's actually going to push up that liquid until it evens out with the liquid in C. So they just have to be at the same height to exert the same pressure. I have one more question in this video. This is another one that I can usually do as a demonstration. I just have a jar of water, and it's on a scale. You can see how heavy it is. And then you put your finger in it. The finger is not touching the bottom. And you have to think before I do that demonstration, well, does anything happen to the scale reading? Does it read more or less or the same weight as it did before you put your finger in? So it turns out that it's actually going to read an increase in weight. Can you think of the reason? Look at this picture. You can see that when you put your finger in, it causes the water level to rise. The water level rises, that means now there's a greater height than there was before. The greater the height of the liquid, the more pressure is exerted at the bottom. So if there's more pressure exerted here due to more force, that means that the scale is going to read a higher reading than when there's less pressure and less force. So that's all for this video. We talked about how pressure changes with depth. The deeper you are, the more pressure. And you just have to remember in a problem, whenever it talks about two different pressures at two different depths, you can use this equation to plug and chug with the pressures. Remember that P2 is the pressure at the bottom, P1 is the pressure at the top.